Purtroppo sono solo un principiante in italiano, quindi devo parlare in inglese, mi dispiace. Grazie per la pazienza. Thanks to Roberto for the introduction and for the invitation to the conference organizers. I'd like to say a few things by way of preamble to the talk, and that the first, as Roberto has mentioned, it's drawn from my 2018 book, Solid State Insurrection, which looks something like this. The second is that I've shamelessly stolen the title for the talk from Ewan Morris's classic, How Physics Became King, which is the other title on the slide. That's deliberate. I'd like to frame this talk, which is about how and why solid state and condensed matter physics grew into the most prominent branches of physics by the end of the 20th century, in the terms that Morris introduced to explain the rise of physics in the 19th century. So in Morris's book, physics was practically unknown at the turn of the 19th century. But by the turn of the 20th, it was the science that people looked to, not just to understand the world, but to manipulate it as well. So its fortunes changed dramatically over the course of a century. He shows how that happens because physicists were successful at carving out cultural resources, building institutions, integrating themselves with the workings of the power structures of society. The story I want to tell about the rise of solid-state physics is similar in some respects, but different in others. So for instance, just as no one in 1800 could have envisioned the heights that physics reached by the end of that century, so too in 1900, very few people could have envisioned the dominance that the physics of materials, of matter, complex matter, would become by the year 2000. But condensed matter physics became king in a somewhat different sense. It was certainly the place people looked for new technologies, but the probing of nature's secrets was still the province of high energy physics and cosmology. So I want to suggest something a little bit different from what Morris did, that condensed matter physics became king in a different sense, in the sense that it reconfigured the physics community as a whole in its own image. And by the end of the talk, it should be clearer what I mean by that claim. So here is a quick plan of the talk. First, we'll turn to the turn of the 20th century and discuss the rise of the pure science ideal, particularly in the American context, which is the specialty of my own research. I will stress that the story I tell here and in the book is principally an American story, and the applicability beyond the US is perhaps something we could discuss further in Q&A. And Giuseppe, the next speaker, will discuss the Italian context in some detail. But for the purpose of this talk, I want to stay relatively narrowly focused on one national context. So after looking at the ideals that helped establish the American physics community, I want to point to some mid-century challenges to those ideals. And that's where this map comes in. I'll talk about it in more detail later. It's from 1939. And what I want to claim is that it's emblematic of a particular way of thinking about what physics was. And that image had to be challenged before we could see the rise of something like solid-state physics. And then in the final two sections, I'll talk about the ways in which solid-state grew through the post-war decades, framed in terms of David Kaiser's work on the post-war population boom in physics, and then look at the transition from solid-state physics to condensed matter physics and what that meant. But for now, let's turn to Henry Rowland, whom we've met once already today. He was one of the few Americans to enjoy an international reputation in physics around the turn of the 20th century. He got it on the strength of his precision diffraction gratings, which Alessandro has already shown us this morning. This one is, I'm afraid, not from an Italian laboratory. This is held at the Whipple Museum in Cambridge. Like most American scientists of note, he got his training in Europe, and he liked what he saw when he was there. So when he returned to the United States to take up a post at Johns Hopkins University, the archetype of the American Research University, he sought to recreate what he saw as a European tradition of elite science. This is what he said in his address called The Highest Aim of the Physicist, which he gave on one of the first meetings of the American Physical Society in his capacity as its first president. He said, "We form an aristocracy, not of wealth, not of pedigree, but of intellect and of ideals, holding him in the highest respect who adds the most to our knowledge or who strives after it as the highest good." This ideal is the ideal on which the American Physical Society was founded. It was self-consciously elitist. It was meant to be, the American Physical Society was meant to be a haven for pure research that would insulate physicists from the commercial incentives that pervaded American society. In practice, what that meant is that this ideology was baked into the core institutions of American physics. And as a result of that, some of those institutions failed to keep up with the demographics of American physics. The charter membership of the APS was small, almost exclusively academic, but through the 20th century, and especially after the First World War, physics was more and more recognized for its practical potential. More and more physicists were finding jobs in industry, for instance. But as this was going on, the people in charge of the power structures of American physics still looked down their noses at any work that smacked of the applied. So this, for instance, is a piece of doggerel that made the rounds at the MIT Radiation Laboratory in the early 1940s, which praised I.I. Rabi for avoiding the lure of industry and sticking to so-called pure work. So it's, now all you bright young fellows with your eyes upon the stars, you graduate assistants who subsist on peanut bars. If industry should woo you with $200 a week, refuse the job and say, without your tongue in your cheek, it ain't the money, it's the principal thing of the thing, and so on, right? So the way in which the culture of these laboratories supported the sort of behavior, rewarded the sort of behavior that would lead to turning down higher paying jobs in industry, devoting yourself to pure research. The upshot is that by the time we get to the end of World War II, physics is suddenly a hot profession. It also has a major rift built into it, dividing the priestly class of pure physicists from the much larger but marginalized class of industrial and applied research. And it's in this context that it's in the context of this rift that we need to understand the emergence of solid-state physics as a discipline in the United States. And it was a strange category, and it was strange because it addressed a very particular need. And this brings me back to this map, which is one of the favorite images I've stumbled upon in the course of researching this project. It was drawn by a physicist named Byrne Porter in 1939, while he was a PhD student studying at Brown University. He's an interesting character, by the way. He's one of the few people to quit the Manhattan Project immediately after learning about the bombing of Hiroshima, and went on to become an outsider artist with a fat FBI file because he kept annoying his neighbors. I like this image because it encodes a particular early 20th century way of thinking about what physics was, right? So Porter has represented, if you can see, the various phenomena of physics as features of the landscape. So you have magnetism, the region of magnetism, you have the region of heat, you have sound and mechanics, and these are held together by the rivers of mechanical and electromagnetic energy. The assumption about physics baked into this map is that when we talk about physics, we're talking about something in the world, right? Physics is out there. Physicists are people who go and get what's out there. This accords very well with the sort of pure science ideal that Rowland was advocating. Physics is in the world. The practice of physicists is pure just to the extent that it is directed toward uncovering and codifying the regularities that already exist in the world. That's what counts as physics. But some physicists would begin questioning this around mid-century. So particularly those physicists who had some stake in technical work. This is just one example. William Hansen, whose work provided the foundation of the klystron, he wrote in a letter to his Stanford colleague David Webster in 1943, responding to a suggestion Webster had made that a physicist should be defined as somebody who seeks the laws of nature. Hansen said, "The truth of this statement depends, of course, on the definition of the word physics. I wouldn't want to attempt a precise definition, but it would seem that your criterion sets the sights terribly high. How many physicists do you know who have discovered a law of nature? You have, I know, and so has Compton and perhaps one or two others, but really this privilege is given only to a very few of us. Nevertheless, the work of the rest is of value." And as you might expect, the rest tended to agree. They formed quite a large proportion of the American community at this time and felt that they were owed something for the contributions that they made. So let's look at this map again. 1939, solid-state physics starts to appear as a discipline in the late 1940s. So let's say it's a decade later, Byrne Porter is trying to update his map of physics. What does he do? How does he represent solid-state physics on this map? there's no obvious answer to that question, right? Because what is solid state physics? Well, it is, we can maybe leave out astronomy, but otherwise it's heat and acoustics and mechanics and optics and electromagnetism and mechanics in solids. So that indicates that it's organized in a very different way from these other phenomenological categories of physics that had dominated the way people thought about the organization of the discipline before the Second World War. The point here is that instead of suggesting that the structure of the discipline should mirror the structure of nature, which is an almost unspoken assumption before this period, the founders of solid state physics were convinced that they could reorganize, the internal boundaries of the field in order to address their transient professional needs. In this case, the need was the need of industrial physicists. They wanted representation in the American Physical Society. They were underrepresented in its journals, mostly because of the elitist foundations of the society, which was organized to cater to academic physicists. There had been efforts to establish a division of industrial physics in the American Physical Society in order to represent the needs of these researchers, but they had been repeatedly shot down by the APS Council on the grounds that it wasn't a topical division. So the division of solid state physics of the American Physical Society, really the first institutional expression of this new subdiscipline, was really a cheeky workaround to the strictures of the APS. The solid state of matter was sort of a topic of physics, as the APS Council demanded, but it was broad enough to encompass most of the problems that industrial physicists were working on at the time. It's one thing during this period if you are employed at Bell Laboratories, which has a quasi-academic environment, a lot of investigative freedom, but if you're working at someplace like even IBM or General Electric or Sperry Gyroscope Company or the Beechnut Packing Company or any other of these dozens of industrial concerns that are hiring physicists, you might well be working on a problem in electromagnetism one week and a problem in optics or thermophysics the next. Your work was not bounded by the traditional topical categories into which academic physicists were sorted. So topical divisions of a professional society would not serve your interest. The flexibility, therefore, of the category of solid state was a conscious concession to the needs of industrial physicists. The fact that this new field served that latent need meant that it grew very quickly. And this is a quick indication of how quickly it grew. This is membership data in the American Physical Society from about the 1950s when these started being formed. This is all of them, all of the divisions. This is division of solid state, later division of condensed matter physics on top. I'll simplify it just to make it a little bit easier to see the relative membership in divisions representing the major parts of physics. There are a couple lessons I think that we can draw from this. The first is that the rapidity with which the division of solid state physics grows, especially in the 1960s when becomes a greater incentive to increase divisional membership, like it taps into a latent need here. There are a lot of physicists, a lot of members of the American Physical Society who regard this area as a key interest of theirs. It was flexible, it could accommodate lively new areas of research such as semiconductor physics. We get the transistor in the late 1940s. Nuclear magnetic resonance techniques become absorbed into the solid state umbrella. The work on the laser and the maser and low temperature physics are all subsumed within this new discipline. The only other thing I'll say quickly about the data is that this systematic drop-off in about 1986 is not an error in the data. That's when the APS started charging $3, I think, for divisional membership. So you ask people to pay a very small amount, and all of a sudden your membership falls to the floor. The other thing I'll bring up here is David Kaiser's work on the post-war boom, the fact that through this period, a great many physicists are being trained. New PhDs are being produced in great numbers. But if we zoom in on that, we see that that wasn't symmetrical. It wasn't as though new physicists were being produced equally in all subdisciplines. So quantitative growth, the kind of growth in the community Kaiser points to, also meant qualitative change. It meant a change in the sorts of interests that characterize the bulk of physicists in the community. That was one mechanism by which physics became, as a whole, became more like solid state itself. It became a loosely linked amalgam of specialties. Okay, so that brings us up to about the end of the 1960s. Population-wise, solid state physics is by far the dominant subfield of physics. It got there because it did a good job representing an active group of physicists who had been marginalized for decades and felt left out of the institutional structure. So it's revealing, I think, that around this time we see a shift in the way that people tend to talk about the field. Instead of solid state physics, we start hearing about condensed matter physics. There are two big parts to the answer of the question why. So this two main characters on your left, Philip W. Anderson, on your right, Brian Peppard. These two had a bit of a disagreement. You see, not all solid state physics was concerned with applied work. Many, such as Anderson, who won the Nobel Prize in the 1977, if I'm remembering correctly, thought that the work he was doing on complex systems was just as fundamental as the work that was happening elsewhere in physics. In the late 1960s, Brian Peppard gave a talk at IBM where he said more or less, look, all the big theoretical problems in solid state are done with. After the BCS theory of superconductivity, he says, there's nothing left of pure intellectual interest. It's time to start training our students just to be technicians. Anderson was having none of this. He wrote his famous article, More is Different, published in Science in 1972, about the emergence of novel phenomena at higher levels of complexity, partly as a response to the sort of pessimism that he was hearing people like Peppard express about the future of fundamental work in the field of solid state physics. So one big reason in this change of the identity of the field, the move from solid state physics to condensed matter physics, is that it shifted the emphasis. Instead of solids, the stuff that's used in technology, it focused attention on condensed matter more generally. It focused attention on the complexity of the systems with which condensed matter physicists were working. And it also coincided with new techniques that made it possible to confront things like quantum fluids, critical phenomena, phase changes, which had strained the credibility of the category of solid state, which people already thought was a bit strange, right? Early classic work in the history of solid state physics is Van Vleck's work on the magnetic susceptibility of gases. So the category was already a little bit incoherent. What else is telling here is that it was possible for Anderson and his allies to distance themselves from solid state because the status of applied work in American physics was secure by this point. They now had a chance to make the case that work on complex matter belonged at the intellectual center of American physics too. Just to finish with some conclusions, I'm not sure if you can read the caption, but this is a cartoon that was published in Physics Today in 1989, I want to say. Two physicists walking away from a radio observatory, and the implication is that there's an older male physicist talking to his younger female colleague saying, I'll be working on the largest and smallest objects in the universe, superclusters and neutrinos. I'd like you to handle everything in between. So this is an indication of how solid state physicists felt they were being pinched at a lot of the time during the 20th century. The prestige has gone to the extremes, and they're stuck working on everything in the middle, trying to make a case for why it's important. The general lesson I wanted to distill here is that this is a story about categories and why they matter, which I think is a big theme for historians of physics. We've heard some of that today about the difference between astronomy and astrophysics, for instance, the way in which those boundaries are constructed. We have this famous line from Dan Kevles, physics is what physicists do, aimed right at a historical audience, right? This scratches the historian's insecurities because the historian will say, well, of course, right? We're not essentialist about disciplines. Of course, we recognize that these are human-built categories, sensitive to all the things that human-built categories are sensitive to. But it does miss something, this slogan. It misses the fact that physicists realized this too at some point, and they acted on it. That's how we get solid-state physics. So this slogan misses the agency that the community commanded to help actively shape their field, which is that we can modify this slogan a little bit and say that physics is what physicists decide it is. That brings some of this agency back in, highlights the efforts physicists made to police and redefine the boundaries of their own field and the boundaries within their own field. The story that solid-state physics tells within the 20th century is that physics in this period, like physics in 19th century Britain, achieved prominence by responding to the social, cultural, and technical priorities at the time, no matter the rhetoric that surrounded high-energy physics. So this is the reason I invoked Morris at the beginning, that this lesson of his about how physics secured authority works as well for thinking about its subdisciplines as it does for thinking about the discipline as a whole. And finally, this highlights how the process of actively remaking the boundaries of physics in response to these social, cultural, and technical priorities throughout the 20th century allowed condensed matter physics to rise to prominence and remake American physics as a whole in its own image. By the time we get to the end of the 20th century, this is a much more diverse, multi-dimensional field, often with very little holding together the various branches. That looks a lot more like solid-state physics than it looks like nuclear physics, cosmology, or high-energy physics. And so on that note, I will say thank you and invite any questions.
Thank you for having accepted the invitation. So we have some time for questions or comments. Yeah, Lorenzo.
Thank you. Very interesting talk. I'm sorry if the question comes from a place of slight ignorance. I'm not too acquainted with the history of physics and solid-state physics, especially in the 20th century. But you mentioned, for example, Bell Labs. So I was wondering if, I know that Bell Labs has several Nobel Prizes associated with it. So I was wondering if you think that the sort of, the spotlight which was granted to solid-state physics was partially a result of the results, the actual scientific results achieved at places like Bell Labs, and if so, what you think were the most significant examples of discoveries or advancements in physics which sort of helped to solidify the status of solid-state physics and condensed matter physics into this sort of greater landscape of physics as a whole. Thank you.
Sure, yeah, Bell Labs is a crucially important institution, and it's sort of unique. There's a great quote from Stefan Matchlup, who was a postdoc there, writing back to William Shockley, who's a supervisor who was collecting testimonials, about what made it distinctive. And what he said was, look, it's not as gemütlich as a college campus, but somewhere in the 2-mile network of corridors, it's the expert on whatever it is you need. So because Bell was a regulated monopoly, right? So they monopolized the telephone system. They produced this sort of basic research laboratory, both as a way of planning long-term for their infrastructure, but also as a ballast against that monopoly. So the fact that you have this incredible concentration of expertise in a laboratory where people don't have very much explicit guidance on what it is they're supposed to be working on, they just sort of hire the people who they think are interested in the stuff that might be useful, it becomes incredibly productive. And of course, that is where the transistor comes from. I mean, that essentially makes semiconductor physics one of the biggest areas of physics almost overnight because of the immediate, obvious commercial potential, but also because it has all these really interesting, it deals with all these really interesting properties of matter that hadn't been explored in that much depth yet. So that contributes to things like understanding of band structure, which is the core of solid state. A little later on, I think in the 70s, it shifts toward things like critical phenomena, where that's a place where people are thinking this has some really profound implications for things like renormalization group theory, which becomes a center of condensed matter physics. So I could give some more examples, but I should probably stop there if you like to talk about it.
Yeah, if I may add, I mean, Bell Labs was, of course, important in this basic research laboratory also before the condensed matter became king, because, I mean, there were also the experiments, but...
In 1930, Clinton Davidson and then,
yeah, exactly. Davidson and Germer.
First industrial laboratory.
Exactly, exactly. Are there other questions? I have a question, which is a curiosity, and then another question. The diagram you showed about the membership in the divisions of the American Physical Society. I mean, did scientists, physicists join more than one division? Could they join? Because, I mean, this seems more or less the same people joining both nuclear and particle, right?
Yes.
It might be that. So it might be that somebody shift. And in any case, I mean, this will make condensed matter maybe even more relevant. Okay, so thanks for this is a curiosity. And while the question was, just a second. I mean, I got your argument about condensed matter becoming king, and I agree. But I'm wondering whether in the US, you compare with the status in other countries, because in Italy, as we will hear in a moment, was quite completely different. So there was a very strong community in nuclear physics, cosmic ray, and then particle physics, of course, etc. And if I'm not wrong, I mean, it was quite, this didn't happen the way you described. So did you compare with other countries, more European, Western European countries, or this is an American story that should be compared in the future with what happened elsewhere?
Yeah, so very quickly on the comparison with other countries, the sort of incoherence I've outlined here in the category of solid state is very much an American phenomenon. The way that solid state gets institutionalized in European countries, so Physik in Germany, for instance, is much more just quantum mechanics of regular crystalline solids. It isn't this big capacious category. It's partly for that reason that condensed matter catches on first in Europe. So that's really a European term that gets imported back into the United States. The United States is very late in accepting condensed matter physics as a category because it has much more robust infrastructure around solid state. So that's very quickly sort of an indication of how the differences in national priorities, national infrastructures shape the way the categories are instantiated and how the back and forth works. But I do think there is more work to be done in looking at, in detail, at how these stories played out in different national contexts.